How do you prevent glitches in logic gate designs? Imagine building a digital circuit that works perfectly most of the time but suddenly gives wrong answers. That's often caused by glitches. Glitches are quick, unwanted changes in the output that happen when inputs change at different times. They can cause errors in digital electronics and embedded systems, especially in complex circuits. So, how do engineers stop these pesky glitches from messing up your devices? Let's find out. First, it helps to understand how glitches happen. When inputs to a logic gate change, they don't always do so at the same moment. Some signals arrive faster than others because of different propagation delays in the circuit paths. If one input switches before another, the output might briefly go to an incorrect state before settling. This is common in circuits where a single input influences multiple paths, especially if some paths include inverters or different types of gates. To spot potential glitches, engineers analyze the circuit carefully. They look at the schematic diagram to see if signals reach the output through paths with different delays. They also use tools like Carnot maps, which are visual ways to simplify logic equations. If a variable appears both inverted and non-inverted in different parts of the equation, it could cause a glitch when that variable changes. One simple way to prevent glitches is to add redundant logic. This means including extra terms in the logic equation to cover all possible input transitions. These extra terms act like safety nets, ensuring the output stays correct even if some signals change unexpectedly. Another effective method is to use synchronous design. This involves registering the outputs with flip-flops or latches controlled by a clock signal. When the clock ticks, the circuit samples the inputs, so the output only updates after all signals have settled. This approach is very reliable because it makes the circuit wait for all inputs to stabilize before changing the output. Filtering is another technique, but it's more common in analog circuits. Using a low-pass filter like a resistor-capacitor circuit can smooth out brief glitches. However, in high-speed digital designs, this method is less practical. Instead, engineers often use strobe signals or enable signals to control when the output is read. These signals ensure the output is only taken after the circuit has stabilized, avoiding transient glitches. Designing circuits with balanced path delays is also key. By making sure all signal paths from inputs to output have similar delays, glitches become less likely. This can be achieved through careful gate sizing and layout planning. Specialized glitch blocking circuits can compare the original signal with a delayed version to detect and block glitches before they reach the output. Techniques like operand isolation and clock gating reduce unnecessary switching activity, which also helps prevent glitches, especially in low-power designs. Using electronic design automation tools to verify the circuit at the register transfer level and gate level helps catch glitches early. These tools simulate how signals move through the circuit and identify potential problems before manufacturing. While adding redundant logic can increase circuit size and complexity, it's often worth it for high-speed or critical applications. In many cases, designers accept that some glitches may occur in combinational logic but relying on synchronous techniques to ensure only stable, correct signals are used. Reducing glitches also saves power because each unnecessary switching wastes energy. So, controlling glitches isn't just about correctness but also about making devices more energy efficient. To sum up, combining careful circuit design, balanced delays, verification, and synchronization techniques provides the best way to prevent glitches and keep digital systems running smoothly.